Myself, Srinivasan, working as a faculty in the Department of Mechanical Engineering at Sri Shanmuga College of Engineering and Technology. Today, I will be talking about convolution neural network. In the last couple of lectures, we discussed about convolution neural networks, where we discussed a lot about what is convolution operation, striding, padding, and all. And these are the important topics that we discussed in the last couple of lectures. Today, we will discuss more of pooling, and it will have pooling layer, and it will have two kinds of pooling. One is max pooling and average pooling. Okay. So before going to discuss about pooling, and we will discuss once again how CNN architecture works. And if you look at the image, that is input image, and as we know, the CNN is used for image and video analysis. We have the input image, that is car here, and it is getting convoluted, and we apply a ReLU function over there, and that will give you the convolution operation will give you the output of the feature map, and there we apply a ReLU function to have the extract the features, and it is again it will go to the pooling layer again, and again it will have multiple convolution and pooling operations. Okay, so once it is done, we will extract the features from the whatever the input image, and that will be flattened, and it will be connected to the fully connected neural network. And finally we will have a output layer where we use a softmax function as an activation function over there to have multiple classes. And based on the probability, we could be able to say whatever we have in the input image is car. Okay, based on the probability, whatever we get. So this is the way it works. And CNN is basically it's a deep learning neural network, and it does both feature extraction and classification. Okay. And since we discussed a lot about convolution operations, now after convolution operations, and we get some feature map, that is output of the convolution operation is a feature map. So where we apply a activation function over here, and whatever the negative value that we have, that will become 0, and whatever the positive value have it remains same. So the positive value represent the we represent the features in the image. Okay. And when you don't use this ReLU function, that all the neuron has to be computed, and all the neurons will computed, and it will be fired, and you'll have a dense computations. So when you apply a ReLU function, most of the negative values will become 0. So, and as a result, we will have 50% or 50 to 60% of neurons will get fired, and finally we'll have better computational efficiency. Okay. So in convolution operation is basically it tries to have the feature map. Okay. And when you apply a ReLU function, it assesses the nonlinearity in the input image, input features, nonlinearity in the input features, and it does the effective intelligent filtering as well. Okay. So whenever we have a weak or irrelevant features in the activation, it will be suppressed by ReLU functions. And very important thing is how many parameters in the neural network. So we discussed in the previous lecture where we focused on multi-layer perceptron. So we focused on how many parameters between input layer and hidden layer. So here also important how many parameters are in a network system, in a convolution neural network systems. So basically, this is the formula that we use. This is the total parameter is equal to that the kernel height and width, and the input channel depth. Okay, number of input channel depth plus this is the bias time over here. This is the output of this output channel, that is the filters. Okay, how many filters that we use. Okay, so this will give you the area of the kernel. I can say KH, and KW will give the area of the filters. And if you multiply with the input image, that is, if you use RGB image, you will have 3 channels, and that will these three terms will give you the weights per filters. Okay, and when you multiply the number of filters, so obviously we'll have the total number of parameters. So this is the equation that we use here. In previous case, previous formula that we used was basically when you give the input image, and what will be the output image when you apply a kernel. Here it is all about the number of parameters that we use in convolution neural network. Okay. So here we don't consider there, we consider striding, padding and all. So here we don't consider all these effects. So for example, if we use a convolution neural network, if you have a convolution layer of 1, that is one first convolution layer, the area is basically 3 into 3 and the number of input channel is 3 over here, the filter that is 64. So you have to multiply all this thing, then that will give you the weights per filters. Then you have to add the bias term over here. And how many filters that we use, that is 64. So these many parameters that we use when you have this size, 1792. Okay. So when you keep on increasing the filter size, obviously your number of parameters will increase. So basically after convolution layer, and we'll have a feature map that has to be downsampled. For that we use that operation is called pooling layer. In pooling layer we use an downsampling operation that will reduce the spatial dimension of your feature map. Basically whatever the output of the convolution is with the feature map, that will be again downsampled by this method, by this method. One is max pooling. Either one can use the max pooling or average pooling. So the max pooling is nothing but when you stride and when you have a filter over here 2 cross 2, and it will take only the maximum value of that particular region. So in this case, if you look at 20 is the maximum one, and if you consider this region, it is going to be 30. For this region, in this case 1 on 12, and this region it is going to be 37. Okay. So basically, this is called max pooling. So we have one more pooling, that is min pooling, that we don't discuss here, and we have average pooling here. The average pooling is basically we have to add all the numbers in the kernel, in the filter window, then in this window, and we have to divide by the total number of elements. So if you do that, and you will have this. This is called average pooling. Okay. So the max pooling is basically wherever we have a strong activations, because it is coming from after loop function. So we have preserved the important features over here. Okay. So it provides a translation invariant. Translation invariant means wherever this objectives are there, and it will extract the features. Okay. So it is basically used for the low level information like edges, corners, and so on. Okay. So suppose if you apply feature map of, this is a size feature map size from the convolution. This is a size 64 into 64 and 60. And if you apply the 2 pi to max pooling, that is 2 cross 2, this is 2 cross 2 window, then if you apply that, and when you stride 2, and what will be the output. So as we know the formula, this is a similar way, similar thing we have discussed. Input 1, that's kernel 1, then we don't have pooling over here, this is stride, then plus 1 will give you this. So then if you do 64 minus 64 minus 2, this is 62 divided by 64 minus 64 minus, this is a size of the pooling one, this one. Okay. And if you do this striding, this is going to be a 31, you will have a 62 will be there, 64, 62, this is 2, this will become 62, then this will become 31. The 31 plus 1 is, this is going to be 32 into 32. The output is going to be 32 into the number of channels, 16. So this is the answer that we get from this. Okay. So that is the purpose of pooling layer. Pooling layer is basically a downsampling operation. It does the downsampling operations. Okay. So this is an important convolution neural network architecture. This is AlexNet. It is developed in the year 2012. It has been it has won for the image recognition. Okay. So where this is conducted in a open forum then in 2012, and it has the architecture of convolution and pooling. So it has 5 convolution operation and 3 fully connected neural network. Finally, we get that 1,000, okay, 1,000 of max functions over here. So basically, we look at, this is the image that we have. There is a digital image. We have 3 channels. That is red, green, blue. Then this is the one. Then when you apply this filters over here, and with that we're going to discuss in the separate summary table. When we'll have this convolution pooling, and finally convolution, and finally if you apply this in one dimensional one, And when you apply in fully connected neural network, and we will finally get the softmax function. Based on this probability, we can able to classify the things. Okay, so this is a architecture for the image recognition. Okay, so as we discussed in the previous lectures, with the first convolution layer will have this is the image that is 22 cross 22 to 227 into 227 into 3. Okay, that is the input image that we have. So there we use this is a kernel size. This is the number of filters that we use. There we use the force striding. Then final output is going to be 55 into 55. So what we have done, we have reduced the number of sizes. Meaning the sample size is going down actually. So we apply the pooling layer again. We apply the convolution layer. So the whatever the formula that we have discussed, the same formula will be used to get what will be the output size of the pooling layer. Okay, in convolution layer. Okay, this convolution layer output size is good. This one, and it will go to the pooling layer where we apply again kernel. Then this will come back to 27 cross 27. Okay, so this is a way it works, and it reduces the sizes. Okay, so we have three fully connected neural networks, and the first one will have 4096 features. Neurons will be there. Okay, so finally you'll have 1000. Okay, and we are interested in an AlexNet, how much parameters we use to get image recognition. Okay, for the purpose of image recognition, how many parameters we use in AlexNet. Okay, so as we discussed in the previous one, this is going to be a kernel one. This is going to be an input channel. Then it is a bias. That is the number of filters that we use. So basically, if we use this and we get this many parameters in convolution layers, so this many parameters are required for the convolution layer. Okay, and similarly, we can go for other things. And finally, if you sum all the parameters, you get 62 million parameters are in AlexNet. Okay, this is an important architecture in CNN that we discussed so far.